Good morning, friends and dear students. I am here for my favorite course, Flight Mechanics. This Flight Mechanics course is related to the 4th semester BTech Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad, India. Today I am going to talk about VN diagram and the flight envelope. So just I will be discussing about this topic, very important topic, VN diagram, where V is the velocity and N is a load factor. So here the diagram which is related to the velocity of the aircraft or the speed of the aircraft and what is the load factor and how much load factor a aircraft can sustain. This we are going to discuss today. I am Dr. Yagya Dutta Dwivedhi, professor from Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad, India. In today's topic, the overview of the topic is steady coordinated turn, charts in conducting their flight operations, VN diagram, load factor, maneuver diagram. These are the points which I am going to discuss, and the last is VG diagram. G is a gravitational force, G force. So, steady coordinated turn, we have seen in the last class also that the steady coordinated turn. So, if we have this is the fuselage of the aircraft, this one, they are the wing here in a normal case, steady level flight, weight will act like this, lift will act like this. If you see from the front, it is a front view. But when we talk about the steady coordinated turn, so your aircraft has to be banked. This is the angle, bank angle phi. This is the bank angle phi. And here if you see now, the lift will not be in the same direction but in this direction, perpendicular to this, and here this will be L cos phi, this one, and this will be L sin phi. So if I make the aircraft and present here, this is the aircraft, and here this is the horizontal line. If I draw here with some blue line, this is the horizontal line here. This is here vertical. This is, I am putting some another color. This is your velocity V line, and this angle is your gamma, that is the climb angle. Okay, this is your climb angle, and this is your here the wing. So if you see here is the weight, lift will be perpendicular to this. This is the lift, and this is this is the gamma, and this is the W cos gamma. This lift has to balance the W cos gamma. And if we take about a vertical turn, it is coordinated turn, means it is in the same plane, and this is the center, this is your R, and if the aircraft is here, assume this is here, so this in this direction, this is the L sin phi, it is shown here in this direction, it is towards the center. And here if you see, this is your V cos gamma. This is the velocity in the direction of this, and this is your radius. This has to be balanced by mv square by r, that is the centripetal force which is balancing this action. So this we are going to discuss. Previously we have discussed this. Now we will see the next. Flight envelope. So flight regime includes all permissible combination of speed, altitude, weight and the center of gravity. This regime is shaped by aerodynamics, propulsion, structure and dynamics of the aircraft. The border of this flight regimes are referred to as the flight envelope, maneuvering envelope. The safety of the passengers are guaranteed by the designer and manufacturers in these boundaries. Pilots are trained to fly within this envelope. Since the aircraft will not be stable, controllable, structurally not strong if fly outside of this limit. So if there is some limitation of the aircraft and if we fly the aircraft within the given envelope, there will not be any problem of stability, there will not be problem of controllability, there will not be problem of structural damages and these all things will not happen. So now a mishap or a crash is expected if flown outside this limit. So if we fly beyond this envelope, there are chances of accident, there are chances of some failure of the component, failure of the wing, failure of the control surfaces or any stabilizer, horizontal stabilizer, vertical stabilizer, elevator, aileron, rudder, any of these things may damage if we fly beyond this capacity. Charts in conducting their flight operations. So first one is the diagram of variation of aircraft lift coefficient versus the Mach number. So there are few very important charts which are used for aircraft design, for aircraft operations. First one is the diagram of variation of aircraft lift coefficient, CL. This is the CL and another is Mach number. CL versus Mach number or CL versus velocity. The second one is diagram of variation of airspeed versus altitude. That is V into H. So how much, at what altitude, at what height, if suppose this is your aircraft and first is the speed. How much coefficient of lift your wings are generating. This coefficient of lift versus how much Mach number or the velocity of the aircraft, how much speed it is traveling. So CL versus V. That is the first diagram which all designers should understand. Second one is the diagram of airspeed V versus altitude. Means at what altitude, how much velocity your aircraft can fly. So, and the next one is the design of variation of diagram of variation of center of gravity versus aircraft weight. XCG versus weight. So I think I will just say what is the meaning of XCG. Weight means the total weight of the aircraft which is supposed to act at the center of gravity. But where is the location of the CG? Here XCG indicates that the location of the CG with respect to the leading edge of the wing. So here if you see, this is the leading edge. Suppose here is your center of gravity. So how much? This distance from leading edge of the wing to this. It is called XCG. So the variation of XCG with respect to the variation of the weight. If you vary, initially when a aircraft is taking off, it is full of fuel, weight is high. As and when the time is passed, the weight of the aircraft will be reduced. So this weight versus the location of the center of gravity is very important parameter for the stability of the aircraft. So then fourth one is very important which we are going to discuss today. That is diagram of variation of load factor, that is N versus airspeed V. So VN diagram, it is called VN diagram. So now we will be discussing about the VN diagram in detail. So this VN diagram is the envelope demonstrated the variation of the allowable load factor. How much it is allowed without any deformation of the body, without any failure of the body. So allowable load factor versus airspeed, that is N versus V. In other words, it depicts the aircraft limit load factor as a function of the airspeed. So V and function of N. So this is called the VN diagram, and we will be discussing in detail about that. So what is the allowable load factor? Allowable load factor is a function of strength of the aircraft. Producible load factor is the function of the engine thrust power. So here one is the allowable load factor. This is the function of the strength of the aircraft. Means it is material strength, how much it can sustain stress, strain, torsion, twist and all. And producible load factor is the function of the engine thrust, and how much load factor it is producing, it is depend upon the how much thrust it can generate. So now I will be discussing the VN diagram in detail. So here is the VN diagram. So here, if you see, this is the 0 here, this is the 0. From here, if you go upward, it is a positive, and if you go this downward, it is a negative load factor. And this horizontal line is the velocity line, and here is a VD, here is a VC, and if you see from here O, A, B, C and D, and here is the corner speed, and this is the special speed here, that is called V star, and here is a VS, this is the stall speed. Here is a star speed, it is a VC. Our aircraft should fly within this limit. Always it is good to fly your aircraft in this range. Also, if you see in this range also, you can fly the aircraft. It is a positive and the negative. You can also see that the negative range is very less comparing to the positive range. Normally it is a -3, and it is here, it is maybe 6 to 7 load factor. For a conventional passenger aircraft, we should have like this. It is a maximum Q, means it is a Q is equal to half rho V square. The velocity and the dynamic pressure is very high in this zone. So if I put here, so this is the red zone here. This area is prohibited area. Your aircraft should not fly in this zone. Now I will discuss about the load factor. There are several forces that are active during a flight operation, such as aircraft weight, engine thrust, lift and the drag. So if you see a typical aircraft, weight will be always acting. To counter this weight, we need a force which is lift. To move this aircraft, we need a thrust, and there will be a drag. So a typical aircraft will have the 4 forces, that is the weight, engine thrust, that is the T, then engine lift, this is lift of the aircraft, and this is the drag of the aircraft. So these are the 4 forces which are acting on the aircraft. The weight of an aircraft on the ground air is naturally produced by the gravity, that is mass times the gravity, that is weight is equal to mg, mass time into the gravity of the earth. There are other sources of load on aircraft during flight, as inertia force, that is the centrifugal force, and gust force. These are the inertial force like centrifugal forces, and the gust load, they are the another type of forces. In some instances of the flight, such as turn and the pull-up, the aircraft must generate a lift force such that it is more than the aircraft weight. So if you want accelerated flight, then lift should be more than the weight of the aircraft. So here N is equal to L by W. For steady state flight, L is equal to W, but for the other flight, L should be greater than W always. This N is equal to, we can also write that acceleration divided by G plus 1. N is equal to AC by G plus 1. Now I will discuss about another diagram, very important. It is called the maneuvering diagram. The VN diagram is basically an envelope that indicates the limits of the load factor and the speed for a safe flight. So we have seen previously that the Venn diagram is related to the load factor and speed, where we have to fly within this given speed limit and with given load factor. It should not increase from the given criteria. The load factor is the maximum allowable N, not the maximum producible N. So here in the load factor which we have drawn is maximum allowable load factor, not the maximum producible load factor, because maximum producible load factor is depend upon the thrust of the aircraft, but maximum allowable load factor is depend upon the weight of the aircraft. This diagram is sometimes referred to as the maneuver diagram. We also say sometimes maneuver diagram. It is usually composed of 3 lines plus 2 curves. So in this we have the 3 lines and the 2 curves. So 3 lines plus 2 curves. So these are the 3 lines we have, 5 lines we have. Out of that, 3 are the straight line and 2 are the curve. The 2 curves on the left hand side represents the aerodynamic limit on the load factor imposed by the stall. So the left side 2 curves are there like this and like this. These curves are depend upon the aerodynamic forces and imposed by the stall of the aircraft. The 2 straight line on the top and bottom represents the maximum positive and negative load factor. The vertical line on the right represents the maximum allowable airspeed. So at the last we have like this line, vertical line. This is the maximum allowable airspeed. Maximum allowable airspeed. Point A is then called the maneuver point. At this point, both lift coefficient and the load factor are simultaneously at their highest possible value. So there is a maneuvering point, that is normally we say the MP. MP is the point where CL, lift coefficient, and N both are intersecting. So this we will see here in this Venn diagram. This we will see that this is the line. This is the velocity where V star. This is the maneuvering point. In this maneuvering point, this is the CL line and this is the N line, load factor line, and both are intersecting, and this is called the maneuvering velocity. And here if you see, I have discussed that there are 5 lines. These are the 2 curve line, 1, 2, 3, 4 and the 5. There are 5 lines. 5 lines have their own, and this VD is the maximum velocity. Maximum velocity. It is also called VNE. Never exceed speed of the aircraft. So this upper side, this is the point here 1, and this is the stall speed. Here the negative, here the stall speed is, for negative stall speed is higher. If you see here, this is the higher. So for going down, negative means nose down. Then you will have like this. So here, this you can see one, here is the Karnal velocity. This is the VC I am writing. Karnal velocity, what is the Karnal velocity? The Karnal velocity is an interesting velocity for fighter pilot and acrobatic aircraft. At a speed less than V star, it is not possible to structurally damage the aircraft due to the generation of load factor less than Nmax. So if you see the previous diagram, and if you fly your aircraft, V star So it is not possible to structurally damage the aircraft. So if I draw again, this is the V star here. This is the V star. So if we fly at V star, your structurally damage will not take place. Very safe to fly the aircraft because aircraft is not generating the load factor more than N max. It is less than the maximum. At speed greater than V star, that is maneuverability decreases since the speed is too high. So if you fly more than this V stars, somewhere here, then maneuverability will decrease. Means the aircraft will not do maneuvering. So V star is the main speed in which aircraft has to fly. This point simultaneously corresponds to the tightest turn and fastest turn of an aircraft. So this V star is called the tightest turn and the fastest turn of the aircraft. The general aviation aircraft like Cessna has a maneuvering speed of 97 knots while its stall speed is 47 knots. Typical Karnal velocity of the current advanced fighter aircrafts are around 250 to 350 knots equivalent airspeed. So 250 to 350 is the best speed for any fighter aircraft to do the maneuvering. So here this you can see the two flight maneuver with a high load factor. A, this is the Lockheed F-16 CS fighting Falcon in an inverted flight. B is the Dassault Rafale in a very high bank angle. It is 90-degree bank angle here and it is an inverted flight here. Inverted flight for F-16 CM aircraft, and this is the Dassault Rafale aircraft which India is also having. It can go 90-degree for a long distance. So inverted flight means if you are flying like this and your aircraft is turned like this and it is flying, it is a inverted flight. F-16 is capable of doing inverted flight for a long time. However, the Rafale aircraft can fly like this and then it can till 90-degree and it can fly like this. That is the specialty of these two fighter aircraft. Now I will discuss another diagram that is called the VG diagram. Here G is the gravitational force and it is also equal to the your Vn diagram only. So here this you can see here normal load factor, it is in the G term, it is 0 is here. This is the minus this side and this is the plus side. Plus load factor here it is shown up to 7, up to 6. So this you can see here we have the different Mach number 2.0, Mach number 2.0, Mach number 2.0, Mach number 2.0. And here is the altitude at 70,000 feet, 64,000, 50,000, 40,000. As you are going high altitude, your zone is increasing. At low altitude, 20,000 feet, you can fly from here to here. Here is 0.1, 0.2. So here Vs for 1G is 200 knots at 30,000 feet. So here the stall speed at 1G we have the 200 knots at 30,000 feet. Vs increases with altitude due to density reduction. As you go high and high, your stall speed will be decreasing. Beyond 740 knots and above 6.5 G and below minus 2.5 G, structural airframe damage may take place. So stay well within this limit. Here VNE, this is the here VNE. VNE is the never exceed speed. Beyond that, structural damage may take place. So here this all your red zone, if you can see here, This all red zone, just I am putting by the green ink. This is not the safe zone for any aircraft. So we should fly in this zone as per given altitude. This is the best zone where our aircraft should fly. So this is the depiction of the VG diagram. It is also equivalent to the VN diagram with some special modification as per the altitude of the aircraft. Now, significance of the military VN diagram. So if we take the military aircraft, what are the new things in that we have to see in this diagram? For the military aircraft, we have very high n is equal to 12 here. So if you can see here, it is 7.5 and here is a -3. Your VN is somewhere 590 knots. This is your VNE. If you see here, this is the A, that is the maneuvering point. And if you drop this line here, somewhere 270 knots. This is the maneuvering speed for the fighter aircraft, which is designed for this. This is the envelope. Your aircraft should be within this limit. If I drop from here, so maximum positive capability from here to here. Unavailable lift area. This area is not useful. This is the danger zone. This area is not useful for flying operation. This area also not useful. This area is also unavailable lift area. Here your lift will be very much less. If your load factor is increasing to this, it is 7.5 and you are going above this, structural failure, damage, positive limits may take place, but if you go beyond this, 100% failure will be there. For the positive, it is 11.25 for a particular aircraft, and the velocity of maximum of for this is somewhere 580, 590 knots. Limit airspeed is 575 knots. Area of structural damage, it will take place here. Positive ultimate strength in this structural damage area, this is the positive limit. Same way, if you see the here, it is the negative limit is -3. This zone is structural damage area, negative ultimate, structural failure area, 100% failure will cause. So this is the one typical VN diagram for a fighter aircraft, and where we have to fly, best zone to fly, I will just again write with a green marking. So this is from here, this area, and here it is best area to fly your aircraft. This is the best safe zone for flight operation. That we have to understand, that we have to fly in this zone only. So factor affecting airplane strength. Factor affecting airplane strength are gross weight of the aircraft, airplane configuration, that is fuel tank, missile loading, etc. Symmetry of the loading due to turn, due to climb, bank, and symmetric distribution, applicable altitude. These are the 4 points which are affecting the things. These are the references from Anderson JD, Aircraft Performance and Design, International Edition, McGraw-Hill's, first edition, 1999. SL by ME, Aircraft Performance, Theory and Practice, AIA Education Series, AIA 2. Any questions, you are welcome to ask. My email ID is yd Dwivedhi, DWIVEDI @gmail.com. This is my email. You are always welcome to ask. Please do like and subscribe this channel. Do comment. If any query, you are always welcome to ask. Thank you very much for the joining my this session. Till then, goodbye. Do like and subscribe. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.